When most people think of evolution, they imagine one species drastically evolving into another, the most common example being the transition from apes to man. Rather, evolution is primarily a process that arises from a mutation or natural variation, allowing the variation to become more frequent, which improves the fitness of individuals. However, one type of selection that challenges the idea is a mechanism called frequency-dependent selection. There are two types of frequency-dependent selection. In negative frequency-dependent selection, the less frequent a phenotype is in the population, the higher its fitness in relation to the other phenotypes present in the population. Due to the high fitness of the less frequent phenotype, it is able to outcompete the other phenotypes and has a better chance of survival and reproduction within a population. However, consider that negative frequency-dependent selection is a balancing mechanism. This means that as the less frequent phenotype begins to increase in frequency within a population, its fitness will begin to decrease. As a result, its own reproductive success will also decrease and ultimately create a pendulum effect. The opposite effect of this is known as positive frequency-dependent selection. In this form of selection, the more frequent phenotypes will have a higher fitness, which allow them to outcompete the less frequent phenotype. Keep in mind that the phenotype itself is not necessarily evolutionary beneficial. Only in the context of the population's phenotypes does it become advantageous or bring about a disadvantage. One of the best ways to identify cases of frequency-dependent selection in nature is to study the bright colors of poisonous butterflies. Let's start by looking at the example of positive frequency-dependent selection. In this example, Central and South American Halocunus butterflies have multiple color patterns, but are all poisonous. Predators avoid the specific color pattern of a poisonous morph that they have ingested in the past. Therefore, the more frequent a morph is in the population, the more likely the bird is to have previously encountered it and learned to avoid it, resulting in the increased fitness of that morph. Mimic butterflies display negative frequency-dependent selection. These non-poisonous butterflies exhibit a phenotype that has developed to mimic the appearance of poisonous butterflies in order to avoid predation by birds. This system is known as Batesian mimicry. When they are rare, predators will avoid the mimic butterflies as if they have already ingested a poisonous morph of the butterflies in the past. When non-poisonous butterflies become more common due to less predation, their population increases, making them more available as a food source. As birds begin to learn that more edible butterflies are non-poisonous in relation to butterflies that are poisonous, the mimic butterflies will lose the element that gave them their previous advantage, causing their numbers to decrease once more. Therefore, the fitness of mimic butterflies is greater the fewer there are. This is where the aforementioned pendulum effect comes into play. The frequency of the non-poisonous mimic butterflies acts similar to a series of waves, rising when they are rare and have less negative factors such as predation, reducing their population numbers, and lowering as they become more common and are therefore more likely to encounter predation. Now that you know that frequency-dependent selection is a major factor that influences the fitness of a species in response to the frequency of its phenotype, this evolutionary process contributes to the survival rate and reproductive capability of many species. Thanks for watching.
Created using Powtoon.